That's it.
Hello everyone. So welcome to the second session of second live session on theory of elasticity. In the last session, we discussed
Sir, আপনার audio আসছে না। ঠিক আছে স্যার, এবারে audio।
Yeah.
The camera.
Yeah. There was a problem in the audio initially.
Yes, sir. It was muted, I think.
Okay.
Sir, we are not getting your audio.
Is it okay now?
Yes, sir. It's fine now.
Yeah. Okay. Fine. Okay. So. Let us start the live session on elasticity, theory of elasticity, live session 2. In the live session 1, there were some technical issues, and therefore we had to stop it. And there are many things that we wanted to discuss, but we couldn't have any time. So what I'll do is, in this live session, we'll address them, and then over last 1 week, whatever confusion, doubt I received, I'll just try to address them as well. So let me share the screen. Yeah. So I hope that screen is visible. See, one confusion is the notations of strain, and we have indicial notation, and then we have tensorial notation, and then engineering strain, tensorial strain. It is essentially they have the similar physicality, but they physical in the sense we compute them. There is a relation between these two strain, and it is just how we represent them in our calculation. Okay, so for instance, if we take just if you take a block, for instance, if you take a small, this is your original length, and then you have x and y. This is x direction and this is y direction. And then suppose this strain is this bar deforms like this. This bar deforms like this. So this, if this is A, B, C, D, and then this become A dash, B dash, C dash, and D dash. So what happens is, this is the thing. Suppose this is D dash. Now, so you have so this is, and so this is, if this is alpha, this is say beta, and this is alpha. Okay, so when we write gamma x, y, this is essentially alpha plus beta, both alpha plus beta. This is engineering strain. Okay. Now, how we write this gamma xy? Gamma xy, if we, for two dimension case, this is del u del y plus del v del x, or del v del x plus del v del y. Okay. This is gamma xy. Now, but then epsilon, if you write it is epsilon xy, then epsilon is xy is written as half of gamma xy. This is half of your del u del x plus del v, del u del y plus del v del x. Okay, so gamma xy and epsilon xy, these two are different representation. Now, if we take it. Uh, Okay, so now what we can do is then if we represent them in initial form, the initial representation will be something like this. Your epsilon ij, that is half of del u del, it is u comma j, I comma j plus u of j comma I. So this essentially means when you write uij, this essentially means del ui del xj. So I and j are the coordinates. So it is xyz, or say 1 2 3, whatever you can write. So if I is equal to x and j is equal to y, then this becomes del u del x, and
Are you there, sir? उत्तम आसन.
yeah, every time there is a problem. I don't know.
Yeah,
Still,
I think your internet is causing some issues, sir.
I don't know. Last time also we had the same issue. Okay, I hope the slides are visible. This, my screen is visible now.
Yes, sir, it's visible.
Is visible, right? My screen.
Yes, yes, sir.
Okay. Okay. I don't know whether it is missed. Another, what we are discussing is the representation of strain, initial representation, tensorial representation. So we just seen that this is how we can write the strain, this shear strain. And then if we have to write, this is gamma xy and this is epsilon xy, and then if we have to represent this in initial form, this is the initial form. Okay. Now the same can be represented as in a tensorial form, strain as a second order tensor. We know that is half of your if you can write half of, that is del of u plus del u of transpose. Del u of transpose, where your del u is what? Del u is the gradient of u. So u is equal to, is a vector, say ux, uy, and uz, and del is again del x, del x, del y. You can write in the vector form. So del u essentially that. So this is essentially, these are the same representation. So this is in a second order tensor form. This is an initial form, right? Now, so then another confusion, another question I received is the, just to the principle of superposition. Explain the principle of superposition. Principle of superposition is, as the name suggests, it is many things are superposed, right? For instance, if I try to explain this through an example in elasticity, if we take if you take a if you take a bar, if you take a block like this, something like this, and which is subjected to some load. For instance, this is, and just take a biaxial state of stress. This is biaxial state of stress, right? So this is now this can be written as you have the same thing, then stress, the response of the system can be the total response of this system. If it is system 1 and this is 2A and this is system 2, the total response of the response 1 and response 2, the system 1 and system 2 both are same. So it is what is the, if you, when you say response, it means the state of stress, state of strains, and then the deformation, both are same. Okay, all are same in both the cases, but remember this is applicable when you are within the elastic limit. But when the nonlinearity comes into picture, then this representation, this is not valid. Okay, so advantage of this linear superposition is suppose if you have a system, then that system is subjected to different kinds of load, different kinds of, you know, the boundary conditions, different types of external forces. Now you may not have to really, but not necessarily that the analysis to be done considering all the forces together. If you are within the linear zone, then what you can do is you can take the individual forces at a time and get the, and do the analysis, and uh, mm, then you can just superimpose them to get the total the response. So this is how the linear superposition is applicable. But remember, this is only valid when you are talking about linearity. Uh, Another thing, the bounds on elastic constant. The bounds on elastic constant means, if you recall, when I say two elastic constants we have for an isotropic material, right? And in the class we discussed how from a general anisotropic material to impose several symmetry, and then finally we get an we arrived at isotropic material. There are two elastic constant. What is Young's modulus, and then another one is Poisson's ratio. These Young's modulus and Poisson's ratio bounds on these elastic constant means what are their possible values, what are their possible values. So Young's modulus, even for intuition, we can say that Young's modulus is, or has to be greater than 0. For that, really, we do not have to go to the equation. It is just by intuition or the sense we have developed. Based on that sense, we can say. But there is another bound on Poisson's ratio. Is the Poisson ratio should be less than, greater than -1 and less than half, right? This is a bound. This is the lower bound and the upper bound. So Young's Poisson ratio cannot be -1 or less than that, and it cannot be half or more than that, right? So what is how we arrived at these bounds? If you recall that if you write the constitutive constitutive relation means the relation between stress and strain in a three-dimensional body. In a three-dimensional body, we have 6 stress components, 3 normal stresses and 3 shear stresses, and then 3 strain components, 3 normal and 3 shear strain. And if you write it, then sigma xx, sigma yy, and then sigma zz, and then you have sigma yz, sigma zx, and sigma xy. You can write it the way you want. Then the point here is, then you have similarly, you have all these strain components, then epsilon xx, epsilon yy, epsilon zz, and then epsilon yz, epsilon zx, and finally epsilon xy. Okay, so you have, if you recall, those components are here -1 by nu, then nu 0 0 0, and so on. So you have a matrix like this. But then outside the matrix, you have elastic modulus, Young's modulus, divided by 1 plus nu, and then 1 minus 2 nu. Okay, now, so what happens, you see here, if you substitute mu is equal to -1, then what, if you substitute, if you take mu is equal to -1 and mu is equal to half, for these two extreme values, what will happen? This is 1 minus 2 nu and 1 plus nu, since we have at the denominator. So this is 1 by, you will have e by 0, which is or very, nu is going to very close to 0.5, or nu very close to -1. So this is very large, and for exactly those values -1 and half, this is infinite. Okay, so which we cannot have this stiffness. But then again, it cannot be less than -1, it cannot be less than -1, because if it is mu less than -1, then 1 plus nu becomes minus negative, so this is constitutive relation becomes negative. Okay, so it is a negative stiffness. So then again nu greater than half, then again because of this term it becomes negative. So from positive definiteness of this matrix, it cannot be, then it cannot be more than half and less than -1. This is how we can arrive at the bounds on the elastic constants. Okay, now then we have stress invariant. We have the stress invariant. Stress invariants are uh, what are the stress invariants? What is the usefulness of stress invariants? You see, when we write a stress tensor, when we write sigma like as a second order tensor. So if you recall, this is sigma xx, and then we have sigma yy and sigma yy and sigma zz, and then we have this off diagonal terms like sigma yx and sigma zx and so on. Okay, zx and so on. Then you have a symmetric matrix here. So now, and then sigma zy and so on. Sigma yx is equal to sigma xy. We can derive this from moment equilibrium. Now, this is when we write stress at a point, express stress at a point by this. This is with respect to coordinate system like this. Okay, x, y, and z coordinate system, right? Now, but then if you change the coordinate system, keeping suppose if I take a different coordinate system like this, different coordinate system, say x dash, y dash, and z dash. Okay, now, but then passing to the same point, with respect to that coordinate system, the stress at this point, the representation of the stress at this point will be different. So at the same point, you have different represent different values of stresses, or this tensor, the matrix, if you write them with respect to different coordinate system, isn't it? Now, but then the individual, if you look at the individual components, individual element in the matrix, they change. But there are, even if you change the coordinates like this, there are some property in this stiffness matrix which are preserved. There are some information of the matrix which is preserved and which is very core to that point, that stress at that point. Okay, and what those properties which are preserved, it doesn't vary even if you change the coordinate system. They are called invariants. Okay, they do not vary, and there are three invariants for this. We'll see that first invariant, the first information which is preserved is the trace of this matrix. Means if you write the stress, if you represent this trace with respect to different coordinate system, but for every representation, your sigma xx plus sigma yy plus sigma zz, they all remain same. For instance, if you write this in with respect to say principal plane, then principal plane is sigma 1 0 0 0 sigma 2 0 and 0 0 sigma 3. So this is with respect to principal plane, principal axis. So sigma 1 plus sigma 2 plus sigma 3, this is the trace of this matrix, and this is equal to sigma xx plus sigma yy plus sigma zz. So this is invariant. Similarly, other two invariants or other two information which are preserved is the summation of the cofactors of this matrix, and then the determinant of this matrix. Okay, determinant of this tensor. So these informations are useful when you talk about, when you read the plasticity theory, and then failure criteria. Failure criteria as a function of different failure criteria as a function of load angles and all. So there we'll see that those things are represented in terms of these invariants. Okay, and okay, so that is the usefulness of the invariants. So if I suggest you to read different yield criteria, failure criteria, and look at how those criteria are represented through different invariants, again different material. Some material may, for some material is where the second invariance is more important. For some material, the first invariant is also important. So again, it depends on what kind of failure is. Sometimes they represent the failure in terms of load angle, which can be related to the third invariant. So it also depends on which kind of material, how you represent those criteria. So there are we will there are uses of these invariants. Okay. Now then uh, then another question. Okay, related to the previous one. Previous question that when we have a bounds on the Poisson's ratio, that Poisson's ratio theoretically it can have negative value. There are materials which can have negative Poisson's ratio, which are called auxetic material. Even the auxetic material, the muscle can have some auxetic behavior, and then in the industry also, people are trying to through some mechanism, of course, auxetic behavior, so that especially if you see the structures which are made to resist or to absorb energy because of impact, okay, where you want that the whatever force you have that to be dissipated over a larger area. So there are those cases, yes, auxetic materials are people are trying to use them, or they form them through some mechanism. Okay, so another question is, you see, related to Aristotle's function. The confusion is Aristotle's function. We have just one, we are solving one phi, but then we have equilibrium equations and compatibility equation. It is discussed in the class that to get the unique solution, you have to get both compatibility relation and equilibrium equation. So if we talk about two-dimensional problem, then we have two equilibrium equations in two axes, and then one strain compatibility equations. We have three equations, and three unknowns are sigma xs, sigma yy, and sigma xy. So then but then you have choices are like this. Either you can solve these three equations to get the now the question is, this is the problem we have, the boundary value problem we have. We have a governing equation, and then subjected to some boundary conditions, force boundary conditions, or your displacement boundary conditions. The point now is how you solve those equations. Okay, solve those boundary value problems, and there are many methods available, some analytical, some numerical methods available to solve them. So Arie's stress function method is just one such method. And what it does is, we assume a stress function. It is called stress function because it is directly related to the stresses. Okay, so what Arie's stress function does is, it combines the compatibility equation and the equilibrium equation, so that eventually you need to solve only one unknown. It is, you don't need to solve many unknown. For instance, this is already discussed in the class. Your sigma x you write as del 2 phi del y2, and then sigma y is equal to del 2 phi del x2, and then sigma xy is minus del 2 phi del x del y. So this is your this is how the stress function defined. Now for a given problem, this is the condition for the stress function, that the stress function has to satisfy this criteria, otherwise it will not qualify as a stress function, right? Now if we combine them, you will see that these automatically satisfy this equation, del sigma x del x plus del sigma xy del y is equal to 0. I am assuming there is no body force, this, and then plus del sigma xy del x plus del sigma y del y is equal to 0. So in absence of body force, they satisfy this equation. If you have a body force, then you have to add another term here, or not here, another term here. Okay, that's it. But they satisfy the equilibrium equation, right? Now then next, once they satisfy the equilibrium equation, then only thing that we need to do is, we need to satisfy the compatibility equation. Now in the compatibility equation is written in terms of strain, and the strain is represented in terms of stress, and the stress is replaced by this Arie's stress function. We get an equation like del 4 phi is equal to 0. The equation is not that simple. If you have a body force term, then you will be having some it won't be 0. There will be term here. Okay. But then if you do not have a body force, the body force contribution is not there, then you have del 4 phi is equal to 0. So this is called biharmonic equation, right? Now if you now then the job is, instead of solving all these three equations, equilibrium equations and compatibility equation, we need to solve this only one equation phi. And if you determine phi, then if you solve this equation, it means the compatibility is satisfied, and by definition the phi satisfy the equilibrium equation. So those equations are satisfied, the basic equations are satisfied. Then when you, then the procedure is used for a given problem, you have to assume phi. uh, then when you assume phi, you should use some information about the, or any information available in the problem. We need to use those information for our assumption. This is a very important thing, because it is not a very, the point I want to make is, it is not mechanical. It is not just phi, you assume a phi, say a fourth degree, fifth degree polynomials, and then if you do that, then you will be having so many unknowns to determine that you may not find sufficient boundary conditions. Then we need to look at the problem. Now, apart from the boundary condition, which are very explicit, then is there any other information I can extract from the problem? This is a very important step. Now, just to make my point very clear, let me give you an example of this. Take again, take a beam problem. This is you have some load here, uniformly distributed load, and then here and here. Okay. Now this is your y-axis. Say you take y-axis upward or downward, whatever. This is your x-axis, right? Now, suppose I want to solve this. Then phi to be written as a function of a polynomial function of a polynomial in x and y, and then every term in the polynomial you have constants. So those constants need to be determined. Then the question is, do we really need to take the entire polynomial, or some of the term we can make, we can avoid, or we can make straight away zero by looking at the problem? You see, what is the, if the phi, if this has to deform like this, then what will happen? The deformation of this beam is symmetric with respect to y-axis. So when you, the deformation at x is equal to x, the deformation at x is equal to minus x, they both are same. If they both are same, then in the deformation equation, the displacement equation should be an even function, right? So if you substitute x or minus x, in both the cases you should get the same value. Similarly, you need to look at whether there is a symmetric in stress or not. For instance, if we take a problem like this, and which is subjected to some load like this, and this is again x-axis, and this is y-axis. This is y-axis. Now we know that sigma x, whether y is equal to plus y or y is equal to minus y, sigma x is same because of the symmetry with respect to x-axis. So naturally, when we choose phi, then we have to straight away make those polynomials which may cause the sigma x as odd function of phi. So we have to look at the problem and see what information we can extract from the problem, apart from the boundary conditions which are very explicit, what information we can extract from the problem. And if we found that some information can be extracted, and we should use those information, we should use that information for our solution. This is not just for this case. Even if you when you in more, even you will be having a finite element course and more advanced numerical computational methods, you will see every time this approximation plays a very important role. We need to start with an approximation, but then this approximation should be as close as possible to the solution. Right now, you can make your approximation better by not just by randomly or just arbitrarily taking a polynomial or whatever function you take, but if you can enrich that your assumption with the information about the problem you have, and what information you have in the problem, that is very much problem dependent, and you have to look at the problem. Okay. Now, for instance, suppose I'm solving a problem like this, a crack problem like this, and just like you have seen towards the end of your elasticity course, and also discussed in the last session, the stress at the tip here is theoretically it is infinite, right? If you have a sharp crack like this, okay, theoretically it is infinite, a very high value. So this is the information you have at this problem, that there is a singularity at the tip of the crack. So if that singularity can be used while forming your or while choosing the field, so that you don't have to really your final solution, you will be very close to the actual solution. Okay, so this is one question. Then another question is plane stress and plane strain problem. It is uh, see, the plane stress, when you say plane stress, it means that your uh, stresses are confined in a plane, right? So you do not have, if you have a x y z axis, then you have all the components of stress in x y and x y plane. All the components are non-zero component, but all the stress components which are associated with z axis are zero, right? So you have sigma xx, sigma yy, and sigma xy are non-zero, and all these sigma xz, sigma yz, and sigma zz, they all are zero. But it doesn't mean that your strains are also zero. Strain in other direction is zero. It doesn't mean sigma z zero. It doesn't mean that your epsilon z is also zero, because epsilon z is a epsilon z. The direct contribution will be zero from sigma z, but then because of the Poisson's effect, you have a contribution from sigma x and sigma y that will generate some strain in the z direction. So similar argument can be applied to plane strain problem as well. In plane strain problem, the strains are confined in a plane, but then you can have stress in the other direction, right? So this is one thing, and then another question is that pure shear, can we have, can is there any example I can cite where your state of stress is pure shear? Means if we see, if we represent state of stress at a point like this in a two-dimensional case, if I show, then this is sigma x, and then this is sigma y, and then we have shear stress like this, like okay, like this was shear stress. This is sigma xy or tau xy. Okay. Now, then pure shear means, of course, you're like this, right? You have like this. Okay. Like this. There is no normal stresses. So, is there any example which where the state of stress is like this? Yes. Suppose if you have if you take a circular shaft and then apply some torque here, this is fixed end. Then if you apply some torque, then at any point, if you see the state of stress, then you will see that state of stress is pure shear. Okay. Then the same with the same flow, there is another question attached to this, that is there any example of where your shear, there is no shear force, only the state of biaxial stress? Yes, again, there is an example. For instance, if I take a cylindrical pressure vessel, and then you have an internal pressure, you have a P, and then if you see, there are hoop stress. This is hoop stress, and then this is your um, um, this is your hoop stress, and then you have another stress. If you cut it from here, then you have another stress on this, right? So one stress along the longitudinal direction, another stress along this direction, circumferential direction. So this is called hoop stress, and this hoop stress is equal to, if you recall, this is PR by T, and this longitudinal is PR by 2T, when P is the internal pressure, R is the radius, and T is the thickness. It is for things, if your thickness is very small, then we can write it. So if we take a body, if we take a small point here and draw the state of stress, then state of stress will be here. You have this PR by 2T for this, and there you will be PR by T. Similarly here and similarly here. So this is state of biaxial stress. Okay. So okay, these are some confusion you had, and then okay. So, for instance, if you have pure shear, then you want to represent this pure shear, then you can represent in two-dimensional case. It will be 0, 0, and then you have only tau here and tau here, whatever shear stress you have, right? Then, if it is biaxial state of stress, then you have then sigma. Sorry, you have, this is your sigma x, and then sigma yy, sigma x is, this is 0. This is also 0. Okay. Now, okay, so these are something that some confusion uh, I received So now that's all. So if you still have any question, you please upload on the forum, and then you can write to me as well. So that I can respond to you in the forum. Uh, there were some questions related to exam. Exam is it will be again your the all the assignments is very similar to the assignments you have. So please, if you do the assignments, and there are very good books available on elasticity. There are good there are many blogs like on mechanics as a whole, like there is a blog called imechanica.org. So all these blogs you can see, you can get what the other people are doing in this field, not just in elasticity or overall mechanics. Okay, with this, since there is no other questions, I'll stop here now. So all the best. Thank you.